Yeah.
That would work, right? Good morning. I think we are ready for the next talk, if this actually works. Not every NIPS has a Test of Time award. So it's a test of time even to get a Test of Time award. This year has one, and the criteria that we decided, or the program chair decided on for awarding it, was 10-year back NIPS papers. So we formed a little committee, and I must say that it was not easy. All the ones that did not get their Test of Time award don't feel too bad. This was not an easy decision, but we did arrive. We did arrive at a paper that we definitely felt was really, really good, and we're happy about it. So let me introduce it. In the author's own word, random features are a trick to speed up supervised learning algorithms so they can operate on big, that is, millions of data point data sets. Traditional learning algorithms work too hard because they optimize parameters that don't actually need to be optimized. Instead, one can randomize over some of the parameters and quickly optimize over the rest. Thanks to the concentration of measure phenomenon, this still provides excellent accuracy. This recipe makes for accurate learning algorithms that run extremely fast and are very easy to implement. So the paper introduced random Fourier feature sampling to efficiently approximate Gaussian kernels. It also introduced random binning features to approximate separable multivariate shift-invariant kernels. Later, they followed up with random stumps for boosting and random support vectors for empirical kernel maps. And from the later variations of this paper follow a very popular term, the random kitchen sink. So without any further ado, in case you shouldn't have guessed what paper it is random features for large-scale kernel machines by Ali Rahimi and Ben Recht. And they are here, both of them. Let's give them a hand. And Ali will be giving the talk. Thank you.
Am I mic'd? Would you mind? Oh, thank you. Okay. It feels great to get an award. Thank you. But I gotta tell you, nothing makes you feel old like getting an award called Test of Time. It's forcing me to come to grips with my age. Ben and I are no longer young, so we decided to name the talk accordingly. We're getting this award for this paper, this first paper up here. But this paper was the beginning of a trilogy of sorts. And like all stories worth telling, the good stuff happens in the middle or at the end, not at the beginning. So if you'll put up with my old man ways, I'd like to take you all the way back to NIPS 2006, when dinosaurs roamed the earth, and Ben and I were young, spry men. Deep learning had just made a splash at NIPS 2006. The training algorithms were complicated, and the results were competitive with linear methods like PCA and linear SVMs. At the workshop, some of us were kibitzing, and somebody pointed out that they should maybe be comparing against nonlinear methods, like SVMs. But of course, at the time, you couldn't scale SVMs up to that size data set. Ben and I had both been working on randomized algorithms separately, Ben for compressed sensing, and I for sketches to speed up bipartite graph matching for computer vision. Once we got home, it took us just 2 emails to come up with a way to speed up kernel machines. These 2 emails became that first paper. The idea was simple. Normally, when you train a kernel machine on a data set, you slap one kernel on top of each data point and associate a weight to each one of those kernels. And you let your optimizers tune those weights to minimize a loss on a training error. Here's the observation in the paper. most of the kernels people were using at the time can be approximated as a straight sum of the product of random functions. If you plug in that approximation in that first equation, you get a linear combination of a straight sum, which is just a linear combination, but one with fewer coefficients to solve for. And that's something the optimizers at the time could handle. The paper provided ways to approximate popular kernels as randomly like this, and also provided guarantees about the quality of the approximation. If you have a kernel and you want to approximate it with such and such fidelity, here's how many random features you need. And in practice, the method worked very well. Now, we'd set out to provide a baseline for deep learning so they could compare against nonlinear methods. But we couldn't find any code to compare against. This was before machine learning was reproducible the way it is now. So we compared against what was reproducible at the time, which was boosting and accelerated kernel machines of various kinds. During our presentation at the poster session, we handed out this leaflet to showcase how easy it was to train large-scale kernel machines. It's a, hey, buddy, you want to train a kernel machine? Here's just 4 lines of MATLAB code. A little bit of a guerrilla marketing for an algorithm. Now, there's something a little shady about the story I've been telling you. According to the bound I just showed you, and that bound is a fine bound, in order to approximate a kernel accurately with these random features, you need tens of thousands of random features. And yet, in our experiments, we were getting away with using just a few hundred features and getting good results. Even more strangely, in some of our experiments, our approximate method was producing lower test errors than the original kernel machine we were trying to approximate. It's always weird when the thing you're trying to approximate does worse than your approximation. This is relevant because back in those days, machine learning had just finished transitioning from what Sam Roweiss used to call an ideas conference into something more rigorous. During the poster sessions, you could see this roving band of what I used to call the NIPS rigor police. They would come to your poster and make sure that your arguments were airtight. I'm thinking of Nati Srebro, Ofer Dekel, some of Mike Jordan's students. If you're unlucky, Shai Ben David. And if you're really unlucky, Manfred Warmuth. But anyway, we decided to send the paper out as is with this dodginess in it and brave the NIPS rigor police. But to do right by them, we eventually came up with an explanation for this phenomenon. And I'll share it with you. Here's the algorithm without any of the kernel flim-flam. Straight up. You just draw a bunch of functions independently from your data set. You weight them, and you tune those weights so that you get a low loss on your training data set. Okay. In the second paper, we showed this. In the same way that Fourier bases provide a dense basis set for an L2 ball of L2 functions, or in the same way that 3-layer wide neural networks could approximate any smooth function arbitrarily well, so too do a bunch of randomly drawn smooth functions approximate densely a function in a Hilbert space arbitrarily well with high probability. So now you don't need to talk about kernels to justify these random features. They don't have to be eigenfunctions of any famous kernels. They're a legitimate basis for learning in of themselves. In the third paper, we finally derived generalization bounds for the algorithm I just showed you. If you have a data set with this many points and you want to achieve this kind of test error on a data set, here's how many random features you need. Now at the time, but by this point, we were now just no longer thinking about kernels. We legitimized using taking a bunch of random kitchen sinks and combining them together, and you don't need to justify that they approximate kernels in any way. So it didn't really bother us if we were underperforming or overperforming kernel machines, or if we had to use fewer parameters or more parameters than a kernel machine. We'd set out on this journey to provide a baseline for deep learning, and we couldn't do it at the time. But since then, the field has become much more reproducible, and various folks have provided baselines in speech where random features are competitive with deep learning to this day. I myself still use random features at work. I like to get creative with the random functions I use and adapt them to the problem at hand. When they work well and I'm feeling good, I say to myself, wow, random features is so powerful. They cracked this data set. Or if I'm in a more somber mood, I might say, this problem wasn't hard at all. Even random features cracked it. It's the same way I think about nearest neighbors. When nearest neighbors does well, you can either marvel about the power of nearest neighbors, or you might conclude that your problem wasn't hard to begin with. Both of these algorithms are good, solid baselines and a way to get a diagnostic on your problem. It's now 2017, and the field has changed. We've made incredible progress. We are now reproducible. We share code freely and use common task benchmarks. We've also made incredible technological progress. Self-driving cars seem to be around the corner. Artificial intelligence tags photos, transcribes voicemails, translates documents, serves us ads. Billion-dollar companies are built on top of machine learning. In many ways, we're way better off than we were 10 years ago. And in some ways, we're worse off. There's a self-congratulatory feeling in the air. We say things like, machine learning is the new electricity. I'd like to offer another analogy. Machine learning has become alchemy. Now, alchemy is okay. Alchemy is not bad. There was a place for alchemy. Alchemy worked. Alchemists invented metallurgy, ways to dye textiles, our modern glass-making processes, and medications. Then again, alchemists also believed they could cure diseases with leeches and transmute base metals into gold. For the physics and chemistry of the 1700s, to usher in the sea change in our understanding of the universe that we now experience, scientists had to dismantle 2,000 years worth of alchemical theories. If you're building photo sharing systems, alchemy is okay. But we're beyond that now. We're building systems that govern healthcare and mediate our civic dialogue. We influence elections. I would like to live in a society whose systems are built on top of verifiable, rigorous, thorough knowledge, and not on alchemy. As aggravating as the NIPS rigor police was, I miss them, and I wish they'd come back. I'll give you examples of where this hurts us. How many of you have devised a deep net from scratch, architecture and all, and trained it from the ground up, and when it didn't work, you felt bad about yourself, like you did something wrong? Please raise your hand. This happens to me about every 3 months. And let me tell you, I don't think it's you. I don't think it's your fault. I think it's gradient descent's fault. I'll illustrate. I'm going to take the simplest deep net I can think of. It's a 2-layer linear net, so identity activation functions. And the labels are a badly conditioned linear function of the inputs. On the left is my model. It's a product of 2 matrices that get taller, and they just multiply the input. And on the right is my loss function. And this is the progress of gradient descent and of various variants of it. It looks like gradient descent goes really fast at the beginning, and then it just seems to peter out. You might say this is a local minimum or a saddle point. That's not a local minimum, and it's not a saddle point. The gradient magnitudes are nowhere near 0. You might say it's hitting some statistical noise floor of the problem. That's not it either. This is not a statistical noise floor. I can compute the expectation of the loss, run gradient descent, and get the same curve. This is not due to randomness. Here's what a better descent direction would do. This is Levenberg-Marcotte. It gets down to 0 loss. It nails the solution in a few hundred iterations, and it gets to machine precision 0. If you haven't tried optimizing this problem, please take 10 minutes on your laptop and just try it. This is our workhorse. This is what we're building models around. You might say this is a contrived problem that badly conditioned something, and just the columns of this A matrix are correlated. That's the only weird thing about it. This is not a contrived problem. You might say gradient descent works just fine on more complicated, larger networks. 2 answers. First, everybody who just raised their hands would probably disagree with you. And second, this is how we build knowledge. We apply our tools on simple, easy-to-analyze setups. We learn, and we work our way up in complexity. We seem to have just jumped our way up. This pain is real. Here's an email that landed in my inbox just a month ago. I'll read it out loud for you. It's from my friend Boris. On Friday, someone on another team changed the default rounding mode of some TensorFlow internals from truncate towards 0 to round to even. Our training broke. Our error rate went from less than 25% error to almost 99% error. I have several emails like this in my inbox, and you can find similar reports on various boards, on various bug reports on the public internet. This is happening because we apply brittle optimization techniques to lost surfaces we don't understand. And our solution is to add more mystery to an already mysterious technical stack. Batch norm is a way to speed up gradient descent. You insert batch norm between the layers of your deep net, and gradient descent goes faster. Now, I'm okay using technologies I don't understand. I got here on an airplane, and I don't fully understand how airplanes work. But I take comfort knowing that there is an entire field of aeronautics dedicated to creating that understanding. Here's what we know about batch norm as a field. It works because it reduces internal covariate shift. Wouldn't you like to know why reducing internal covariate shift speeds up gradient descent? Wouldn't you like to see a theorem or an experiment? Wouldn't you like to see evidence that batch norm reduces internal covariate shift? Wouldn't you like to know what internal covariate shift is? Wouldn't you like to see a definition of it? Batch norm has become a foundational tool in how we build deep nets, and yet as a field we know almost nothing about it. Machine learning has taken a new spot in society. If any of what I've been saying resonates with you, let me offer just 2 ways we can assume this new position responsibly. Think about in the past year, the experiments you ran where you were jockeying for position on a leaderboard and trying out different techniques to see if they could give you an edge in performance. And now, think about in the past year, the experiments you ran where you were chasing down an explanation for a strange phenomenon you'd observed. You were trying to find the root cause for something weird. We do a lot of the former kind of experiments. We could use a lot more of the latter. Simple experiments, simple theorems are the building blocks that help us understand more complicated systems. Here's a second thing we could do. Right now, our mature computational engines that run on commodity hardware are all variants of gradient descent. That's what we have that can handle tens of billions of variables. Imagine if we had linear system solvers or matrix factorization engines that could handle tens of billions of variables and operate on commodity hardware. Imagine the amazing kinds of optimization algorithms we could build. Imagine the incredible models we could experiment with. Of course, it's a hard math problem and it's a hard systems problem. But this is exactly the group that can solve these problems. Over the years, many of my dearest relationships have emerged from this community. My affection and respect for this group are sincere, and that's why I'm up here asking us to be more rigorous, less alchemical, better. Ben and I are grateful for the award and the opportunity to have gotten to know many of you and to have worked with many of you. And we would love it if we could work together to take machine learning from alchemy and into electricity.
Thank you so much for this talk. I hope that we'll be able to give you a new award in 10 years from now for the return of the rigor in the NIPS community. We have time for probably one question or two. Wait. Oh, yeah. Okay. Since we are all just stunned by the message here, which we all appreciated so much, I just want to invite Ben up here as well, so I can hand you the official certificate for the Test of Time Award. So hereby it is the end of the Test of Time Award, and the program continues on.
Thank you, Sam.
I think there's a break now, so we